Hello, I'm Mr. McBrien, and this is TEJ3M, Transistors, the Magic Sandwich. So transistors, we've already discussed briefly, and they're pretty much the most important innovation of the 20th century. They're incorporated in pretty much every commercial electronic device. And they're a little bit inconvenient for us because they're semiconductors. They're another device that doesn't follow Ohm's law. However, if we know a little bit about them, we can incorporate them into our devices the same as commercial manufacturers have done with theirs. So none of that tells us what a transistor is. And this is what is the 2 hours traffic of our stage. I promise not 2 hours. We have various kinds of transistors that we can discuss. We're going to focus on a specific kind. We'll get to that in a minute. We're going to talk about the different transistors, how to select them for the purpose we need, how to incorporate them into schematics. We're going to talk about their use in modern electronics. It's important that we discuss the first transistor in order to get a context for what we're doing. Okay, so the purpose of transistors. Transistors can be used as an electronic switch or they can be used as an amplifier. And as such, they get incorporated into important applications like microprocessors. Our CPU chips have, you might recall, a couple of billion of transistors on them. They're incorporated into cell phones. And we'll use them in motor controllers and things like robotics. Now, as far as the history of transistors go, we need to, before we talk about transistors themselves, talk about what was used before them. So before transistors, we had vacuum tubes, and vacuum tubes were similar to transistors. They were used as signal amplifiers and as switches, and they were awesome. They could work at high frequencies, they could handle high power, they were compatible with high voltage, and you may have heard of these things, electromagnetic pulses. They're less vulnerable to those as well. However, they had key disadvantages, and this was why transistors were so important. They're very large and very fragile, so they're made of glass. They are macroscopic devices, so a single vacuum tube would weigh a fraction of a pound. They need tons of energy, so they use up a lot of energy in their working, and they're also expensive. So these disadvantages created a real problem. Now, in order to understand the context of this, we were, around the end of the Second World War, starting to flirt with ideas like jet propulsion, rocketry, sonar, radar, and these kinds of things. Now, all of these needed decision-making systems, so electronic systems for amplification and for control. But at the same time, there was a need for small, lightweight devices. And vacuum tubes were not that. So there was a clear need throughout the world of a device that was small, tough, reliable, and energy efficient, and also cheap to manufacture. Luckily, along came Bardeen, Brattain, and Shockley. And in 1947, they invented a transistor. And they described the transistor effect in this way. When electrical contacts were applied to a crystal of germanium, the output power was larger than the input. Now this was an extremely exciting result, but not quite as exciting as it might sound in first pass. And you'll probably get a feel for that at the end. What we do need to be clear about was this was not a source of free power. Rather, it was the capacity to control power. And we'll understand that in a second. Okay, but once they had this amplifier switch, once they had the capacity to make this tiny amplifier switch, all of a sudden a new age opened up. We had the capacity to build all kinds of amazing things that were impossible before that. And really, the ensuing 53 years and the time since then has been spent learning how to use that amazing transistor. And all of the inventions you see on the screen are impossible without that transistor. Okay, so what was the physical basis for this shocking device? Well, first we have to know a little bit about doping, not the athletic doping, but rather semiconductors, in which we introduce impure elements into a semiconductor wafer, and that gives us a region of differing electrical conductivity. So we have two kinds, an N-type, in which negative free electrons are the impurity in this lattice, and P-type, in which positive holes are contained as an impurity in this system. So the effect of this doping are positive semiconductors, our P-type semiconductors, have a few electrons removed from the lattice structure, and our N-type semiconductors have unbound electrons that have a negative charge in the lattice structure. You might remember this is closely related to the way electricity is conducted in metals. Now, neither of these is particularly interesting on its own. It's just a material that doesn't conduct electricity very well. The magic starts when we put one of each of these in contact. We get a PN junction. And that PN junction, if we have a forward bias in which the negative potential is at the N side and the positive potential is at the P side, we see a system where electricity can be conducted. So electricity can flow. Our electrons flow from the negative terminal of the battery through the N-type semiconductor, and they move towards the holes on the P-type semiconductor, and they meet in the center. And this is great. We get conductivity. And it wouldn't be that exciting except for what happens when we reverse the voltage. When we reverse the voltage and put the positive terminal to the negative side, we see a system where the electrons are pulled away, but there's no electrons replacing it. And our conga line principle means that the electricity is going to stop flowing. Similarly, the negative terminal of the battery pushes electrons towards the holes in the P-type semiconductor, but there's no way for those electrons to move through it. And so what happens is we get this depletion region here. We get this depletion region, and electricity ceases to flow. Our conga line can't keep going. Now, those of you who remember a few days ago will say, wait a sec, isn't that just a diode? Electricity can flow one direction and can't flow the other? And absolutely, this is a diode. So what's interesting about this? Well, what's interesting is when we make two PN junctions instead of one. So we essentially make a sandwich of positive material surrounded by negative material, or negative material surrounded by positive. In this case, if you think this through, and if you draw the diagrams like you saw in the previous slide, you'll see that the potential applied in one direction will result in temporarily in a little bit of flow that almost immediately stops because it reaches the next junction. But the same thing happens for the other one. Essentially, electricity can't flow in either direction. So by putting two diodes against each other in that way, We've made it so that electricity can't flow in either direction. Not very interesting. Except for one thing. What we can do is attach another electrode directly to the center of the sandwich. And we call this electrode the base. And once we do this, we can use a potential at the base to control current flow and amplification. So let's have a look at one of these in action. This is a BC547 transistor. All right. It's an NPN transistor, meaning that it has negative N-type semiconductor on either side and positive in the middle. Now the data sheet will tell us how to configure the pins, but we can look at this and we can see that the current flow needs to be this way based on the arrow that's in the schematic, the symbol. So we put positive on the C, the collector, and we ground the emitter, and no current flows. But this is only the case when there's no potential attached to the base. As soon as we apply a potential, a positive potential to the base, our resistance of our transistor goes from being very high to being very low. So this is the situation of our apply a small current to the connection and get a large current. So we put a small amount of power into the base and it drops the resistance of the transistor down to essentially null. But because it's attached to a power supply, we can get lots of power from a tiny amount of power. Okay, so there are literally thousands of different transistors. So what's the difference between them? What makes them different? What makes them unique? Well, they're made of different semiconductor materials. They're structured differently. You can see some of the structures here. You can have PNP versus NPN. You can have its maximum power rating, its operating frequency. All these different things apply. Also an amplification factor that we'll investigate at a later point. So we choose our transistors based on all those different characteristics. Now, if we want to wire our circuits with our transistors, the answer to how to wire them depends on the data sheet. We're going to focus on the specific kind of transistor here, our BJT transistors. So what we can first look at is what we call operation modes. Now the operation modes, there are three important operation modes for us to consider. The first is when we put a very low potential. For our purposes, we can consider that potential to be zero. We put a low potential onto our base of our transistor. When we do this, all right, when we apply a low potential to it, the current to the base goes to zero, and we call this cutoff mode, no current flows. This is our case where the resistance of our transistor is very high. Now, if we increase that potential at the base to greater than 0.7 volts, suddenly the operation of this transistor changes, the mode changes. If our current is small, we get an amplifier. Small increases in the, or let's call it proportional increases in the base current, give us proportional increases in the collector emitter current. So it functions as an amplifier. If we double the current to the base, we double the current through the transistor. And this active mode, forward active mode, works like an amplifier. Now there's a different active mode that we can talk about. So this is a case where we have enough potential to make the transistor work, but we increase the current to a relatively high level. So at some point, the transistor no longer amplifies, it's simply on. It's saturated, it's the maximum current that it can support, and increasing the current to the base won't increase the current through the transistor. So this saturated mode is essentially the transistor is giving us the most it can. Now you should be able to understand how a transistor can work as a switch or as an amplifier. If we skip over this small current level and we go from no voltage applied to B to potential applied to B and a relatively high current, the transistor turns on. If we keep the current low but have a high potential there, relatively high, 0.7 volts, then it functions as an amplifier. So we get to choose how that transistor works. So just to reiterate that, if we want to switch between modes, the first thing we need is a forward bias. This turns our transistor on at some level. It goes from cutoff mode to active mode. Now we control the resistance of the transistor with the current to the base once we have that potential there. So how do we control current? The answer, of course, is with a resistor. So if we want to control the base current, we can use a resistor connected to our base to control that current. So we know we need the potential. So the potential is being provided by our battery here, and our push button switch will turn on our transistor. So then this resistor R1 here will control the current and decide what kind of mode we have. Incidentally, if we omit this resistor altogether, most transistors will burn out. So they can't handle that much current. So we put a large resistor here. It's typically large because we only need to remember Brattain and Shockley told us we only need a small amount of current to allow current to flow through this transistor. So we use a fairly large resistor to make sure that the current is very low to the transistor. So R1 might be, a typical value might be 100 kilo ohms. Now the exact value for that depends on the transistor itself. Now we have to pay attention when we have our transistors in place. We have to pay attention to which kind we have. So if we have an NPN transistor, the wiring requirements are different than for a PNP resistor. So for NPN, we apply a positive potential at the base in order to send its resistance low. For PNP, it's the other way around. We apply a negative potential at the base. Now, other than that, the operation is pretty much the same. So we still need to control current in the same way, these kinds of things. Now, you should note above that the collector and emitter pins are reversed on the schematics that I've shown in the top right corner of the slide. You need to confirm the pins for your transistor, and you need to remember that the arrow points in the direction of current flow. So you want to triple check these things on your data sheet before you construct your circuit. Now the schematics for these transistors all reflect the one-way current flow nature that they exhibit. So key points then from our discussion today. Transistors are the basis of almost all modern technology. They function as an electronic switch or amplifier. An applied potential to the base will turn them on. A small amount of current will then control a larger amount of current. Now PNP and and NPN transistors work in a similar but different way, and you need to keep that in mind when you're working with them. Thanks very much. Have a great night.